Indeterminate forms. Okay, I'm going to say a bunch of stuff here that's going to be clearly not testable. It's just to orient you or explain certain things. You notice we don't get you to prove much on tests, so don't panic about this. Pick up some of the big ideas or parts of this. All right, ready? Okie dokie. What are we going to talk about? We're going to talk about a familiar indeterminate form. We're going to talk about using linearization to figure this out. We're going to talk about L'Hopital's rule. And then we're going to talk about indeterminate products and differences. Here we go. Recall that function. Okay, way back when, I showed you this as an example of a removable discontinuity. Okay? This function isn't defined there because you'd be dividing by 0, but it has a really nice limit there. Okay? In fact, the limit as x approaches 0 of this function is, what is it? Thank you. Okay, you're approaching 1 as x approaches 0. Excellent. All right, this is really important when you're trying to prove what the derivative of the sine function is. All right, we don't do that in this class, but if you wanted to prove that the derivative of sine is cosine, you'd probably use this fact, and others. Also, I mentioned this in the context of the small angle approximation, that for small x, sine x is approximately equal to x. And that's going to come up again in a minute. Okay, so what did we do to try to figure out this limit? We just looked at a computer-generated graph, okay, and we hoped that it wasn't hiding anything from us, okay? That there weren't any computational problems, that the resolution of the graph didn't trick us, that our eyes didn't trick us, that nothing surprising was going on in here that we're missing, okay? But how can we know for sure? Or roughly for sure? We can't use the limit laws in this kind of situation, because what's going on? The limit of this guy is 0, okay? Limit laws don't like that. So the bottom's going to 0, so the limit laws are impotent. So, when we have a quotient where the top goes to 0, and this is a really hard piece of stuff. Okay, where the top goes to 0 and the bottom goes to something non-zero. Okay, the top goes to 0 and the bottom goes to something non-zero. We know that the ratio is going to go to 0. And you've seen that before. We know that if the top goes to something, what am I? Okay, good. When the top goes to something non-zero and the bottom goes to 0, we have some kind of does not exist. Okay? Either it's going to infinity or it's going to minus infinity or it just doesn't exist. Okay, we've seen examples of that before. If that doesn't make any sense, let me know. What's the problem here? Both the top and the bottom are going to 0. Okay, right? As x approaches 0, both sine x goes to 0 and x goes to 0. So it's neither of these cases. Okay? Top and bottom go to 0. We can't conclude anything from that. So it's called an indeterminate form. So if the top goes to 0 and the bottom goes to 0, that's not enough to conclude anything. Okay, the limit might exist, it might not exist. Okay? I've written it out in full there. Okay, this applies to one-sided limits as well, and it applies to limits at infinity as well. If the top and the bottom both go to 0, you have what's called an indeterminate form of type 0 over 0. Okay, that 0 over 0 is a description of how this thing is behaving in the limit. Again, the limit may exist, it may not exist. So you need some way of figuring out which it is. All right, in this case, we've already talked about how to figure this out, and so we'll do it one more time. Okay, so we want that limit as x approaches 0. Okay, so let's see what these guys look like near 0. I'll leave that up for another second. Okay. Okay, near 0. Okay, for x near 0, sine x is approximately x. Okay, we talked about that, the small angle approximation. Okay, or in other words, what am I saying? As I get closer and closer to 0, sine x gets arbitrarily close to its linearization, centered at 0. Okay, which was x. I'm going to go to the next slide now. Okay, so as I get closer and closer to 0, the curve is arbitrarily well approximated by that tangent. Okay? And that's where I care about. I care about what's going on near 0 as I get closer and closer to 0. Okay? So I get closer and closer to 0. Sine x becomes essentially indistinguishable from x. Okay, so sine x looks more and more like x. And if we're dividing that by x, we're just going to get 1. Again, what did we do? We linearized this guy around that point, wrote it there, and something nice happens. That's just 1, and the limit is 1. That's not really a proof either, but it's getting there. Okay, it's better than just looking at a picture. Okay? Again, don't obsess about that, it's just an example. Okay, indeterminate forms of type 0 over 0 are not exactly rare, okay? Hey, here's a thing. Okay, the definition of the derivative at a point. Wherever this exists, you've got an indeterminate form of type 0 over 0. Okay? Every single derivative you've seen is fundamentally indeterminate of type 0 over 0. So this is an important object to be talking about. Okay. Let's generalize what we did here. Let's generalize a bit. Okay, we'll do the same thing we just did here. It's color time. Okay, suppose. What have we got? F at A equals G at A equals 0. The derivatives exist and the bottom derivative is not 0. Okay? And suppose we want find the limit as x approaches a of f at x over g at x. Okay? This winds up being indeterminate of type 0 over 0. Okay? So what can we do? Let's try doing what we just talked about. Okay, this picture doesn't much matter, so say that's A. Let's say that's F. And hopefully this looks different. Okay, and that's G. Okay, at A they're both 0. They're both differentiable, and this guy's slope is not 0. Okay, so this is what we're talking about. We want to find out what happens to the ratio of these two guys as we get closer and closer to A. Okay? Okay, same thing. We want to talk about what goes on as we approach A, so let's talk about near A. Let's talk about linearizations. Okay, zoom in. much. Okay, that's A. Okay, if I zoom in enough, again, the differentiable, they look essentially like lines if I zoom in enough. They look like they're linearization, so let's look at those. What do we got? F looks like that. Okay, F, or the linearization of F, looks like that. G looks like that. Okay, if I zoom in enough, they get as close as we want to their linearizations. Okay, this is just to explain where future stuff comes from. Okay, don't panic if this isn't making sense, but if you want to know and it doesn't make sense, just let me know. Okay, that's all good. Okay, this is X. All right. That's where F is at a particular value of X, okay? And that's where G is, okay? What can you see? These are essentially lines, okay? The slope of this is the derivative of F at A. The slope of this is the derivative of G at A, okay? You can convince yourself, because you're looking at the same run, okay, that the ratio of heights, okay, the ratio of these two heights is just about the ratio of those rises of the lines. And because the run is the same, the ratio of the rises is just the ratio of the slopes. And what's the ratio of the slopes? The ratio of the derivatives. Okay. I'll put another one in here. The ratio of heights is F at X over G at X. Okay, so the ratio of F to G, the ratio of the heights, because the run is the same, is roughly the ratio of the rises of those lines, which is equal to the ratio of their slopes. Again, because the run is the same, the ratio of the rise is the same as the ratio of the slopes, and so we just get that. Okay? Or if you want to think about it the way I think about it, we'll use differentials. That's dx, small change in x. Okay, that's dg. That's df. Okay, just the stuff we talked about last time. Okay, so if you write it like that, you can see that f at x over g at x, okay, is approximately df over dg in this case, because we're starting at height 0, is approximately df over dg. What do we say this was? Derivative times dx. This was derivative times dx. The common run cancels, and we just get the ratio of the derivatives. Okay? Don't freak out if this doesn't make sense, but ask me if you want. Okay? Again, because we start at height 0, the ratio of the heights is just the ratio of the slopes because we have a common run. Okay. Okay, this is good for small dx. In the limit as dx goes to 0, this approximation becomes exact. Okay, the functions look more and more like their linearization, so in the limit, the approximation becomes exact, and we wind up with this. Okay? Okay, I put two other versions in the slides for you. Please don't try writing this down now. Two other versions. This is again based on linearizations, but it doesn't talk about differentials, so you might like that better. Okay, and you get that result. And this is an algebraic version, so if you like just doing algebra without talking about linearizations, you can use that. It just uses the definition of the derivative and a bit of algebra, and you get the same result. Okay? Okay. This thing, okay, under these assumptions, is a special case of L'Hôpital's rule. Okay, originally spelled with an S. This was published by Guillaume de L'Hôpital in one of the first textbooks on calculus. Apparently a very good textbook. And remember what I said, the name doesn't always tell you who actually came up with it, and Johann Bernoulli actually came up with it. Okay? So this guy got letters from Johann Bernoulli, and then he just put the stuff in his textbook, and so now it's named after him. Okay? He never actually claimed credit for it. He was honest about it that way, but we still name it after him. Yeah. Okay, so here we go. Suppose that limit of that quotient is an indeterminate form of type 0 over 0 or infinity over infinity, which I haven't mentioned yet. So I said if the top, where am I going? Okay, so I said your indeterminates of type 0 over 0, if the top goes to 0 and the bottom goes to 0. Okay? Indeterminate of type infinity over infinity means the top goes to plus or minus infinity and the bottom goes to plus or minus infinity. Okay, so if you have an indeterminate form of either of those two types, either the one we've talked about the whole time or that infinity over infinity one, if near A, f and g are differentiable and the derivative of g is non-zero, then we get this. The limit of the quotient is equal to the limit of the quotient of the derivatives, provided that latter limit exists or is infinite. And you can use this for one-sided limits and limits at infinity as well. Okay? This was a special case of that. Okay? You'll notice that has an extra lim than this does. Okay. What do I want to say? So, if the top and bottom both go to 0 or both go to one kind of infinity or another, then what do? You apply L'Hopital's rule, you take derivatives of top and bottom, and then you take the limit of that. Okay? And you see what happens. This is not quotient rule. Okay? You take the derivatives of the top and bottom separately and you divide them. There's no quotient rule going on. Life's good. This thing, I've made this as simple as I possibly could, okay? And this just says don't do anything stupid, okay? F and g have to be differentiable, obviously, otherwise why are you taking the derivatives? And this is just saying don't divide by 0. So there's nothing very exciting going on there. What else? Don't ever apply L'Hopital when that isn't going on, okay? Only apply L'Hopital's rule if you've got 0 over 0 or infinity over infinity. Please write that down, don't make that mistake. You can't just use this as a catch-all rule for everything, okay? If you try, you will get wrong answers. Okay? This thing only works, or is only guaranteed to work when you've got those kinds of forms, okay? And again, note the limit laws are impotent in this case. Impotent, not important. They're useless in this case. Because in the limit laws, your limits have to exist. Okay, so that case is not going to work with limit laws. And this case is not going to work with limit laws because you can't divide by 0 in the limit laws. Okay? So this is a new, more general, systematic tool to deal with indeterminate forms that the limit laws can't handle. Okay, one more minute. What I'm going to do is I'm going to do an example. And in tutorial, I'll do some more examples, and on Wednesday, I will sum up some of the stuff. So here's an example we've seen to death. The limit as x approaches 0 of sine x over x. Okay. As x approaches 0, sine x approaches 0, always check these things, okay? Otherwise, you'll be using this thing when you're not allowed to. As x approaches 0, sine x approaches 0, and x approaches 0. Okay? So we have an indeterminate form of type 0 over 0. So yes, we're allowed to use L'Hopital's rule. So that limit is equal to the limit of the quotient made up by the derivative of the top. The derivative of sine is cos. The derivative of x is 1. As x approaches 0, cos x, being continuous, approaches cos 0, or 1. Really, really easy, okay? Don't go thinking this is a substitute for proving that limit from scratch, okay? Because to do this, we needed the derivative of sine. And you need this to find the derivative of sine, okay? So we cheated, this was dishonest, okay? But at least it's a way of showing this and demonstrating L'Hopital's rule. Okay guys, I will see you on Wednesday, and some of you I will see in tutorial. Have a lovely day. Okay, this is L'Hopital's rule again. And I said we use this, or we can use this, when you have indeterminate forms of type 0 over 0 or infinity over infinity. Sometimes you have that indeterminate form, and you don't have to use L'Hopital. Okay? And when you don't have that indeterminate form, definitely don't try to use L'Hopital, or you can get wrong answers. Again, this is going to be a very, very, very quick review of this. I listed the types of indeterminate forms. You shouldn't have to write this table down. Everything's natural, okay? If you've got something going to 0 up top and something going to 0 on the bottom, then you call that indeterminate effect 0 over 0. And the other forms, or the other indeterminate forms I talked about, just make sure you're familiar with them. Again, you don't have to write down the whole table. Just understand what's going on. By the way, I listened to the tutorial video and I was talking even faster than usual. So if I'm talking so fast that you can't understand, please stop me. Okay, here's an example we did. And so in the case of this limit, that top blows up and the bottom blows up, and so we have infinity over infinity, and we can use L'Hopital's rule, okay, to find the limit as x goes to infinity of that ratio. And in general, we can use L'Hopital's rule to show that logarithmic functions, as I explained before, grow very, very slowly, and in particular, ultimately more slowly than any power function, including the root function. We did this example, comparing an exponential to a particular power function as x grows large, and again, you could use L'Hopital's rule for that. And in general, you can show that the exponentials are faster, ultimately, than the power function. Okay, so the exponentials are very, very fast, the logarithms are very, very slow. We talked about how there were indeterminate forms that aren't quotients, so indeterminate products, where one factor in the product is trying to pull you down to 0, and the other factor is trying to pull you to infinity or minus infinity. And the trick there was to try to rewrite the thing as a quotient. Okay, so to try to rewrite the product as a quotient, to which you can then use L'Hopital's rule. And that's it. So an example of that was x ln x, as x approaches 0. You rewrite that as a quotient, you apply L'Hopital's rule, and you get an answer. Proof by picture. And the final case we did was indeterminate differences, where you have two terms subtracted from each other, and the two terms go quote unquote to the same kind of infinity. And there's a number of tricks you use, again, to try to rewrite the thing as a quotient, to get an indeterminate form you recognize and that L'Hopital can tackle, and then you use L'Hopital's rule. And that's the example we talked about there. And the trick we used was, it's not much of a trick, you just write that over a common denominator, apply L'Hopital twice, and you've got an answer. Okay? So again, L'Hopital can be used a bunch of times in sequence if necessary. Sometimes it takes reasonably clever rewriting to be able to apply L'Hopital's rule. And finally, don't use L'Hopital's rule if it's not valid, okay? Because you'll get wrong answers, typically. Okay, again, if you've got any questions, talk to me or see the video, see the slides. Okay? Questions?